Welcome to our talk on, say, voice over IP security with some special focus on certain technologies in it. I'm Enno. This is Daniel. We both work for a German security consultancy called ERNW. We are both, say, old school networkers, and some of you might even know us from previous talks at Black Hat. Today's talk is going to cover, say, three sections. The first is we want to introduce some what we call the seven sisters. That's basic infrastructure security elements that apply to any type of complex environment, which might be a network, which might be, say, a harbor or an airport or whatever. And those can be applied to voice over IP as well. That's what we, to some degree, do in a second part, where we give some case studies from environments we practically assessed. And the third piece, probably the one that some of you might be waiting for most, will cover a certain technology and what we think are flaws in that technology. Let's start with the seven sisters. Those are, again, 7 infrastructure principles that, and I repeat myself, can be applied to any type of complex environment. That can be used as a kind of checklist once one wants to implement security in some complex setting. I won't explain them in too much detail. I'll go through them quickly. We have there's a blog post where we explain them in a bit more detail. The first one is, say, access control, so limit who can take part in, say, an environment or in technology or in a certain communication act. The second is isolation. Once there is, within a complex environment, there's things that behave differently as for their protection need, threat exposure, or their trustworthiness, it might be an idea to isolate them from each other. The third principle is a restriction. Once you have isolated entities, usually there is intersection points, and at those intersection points you can perform security operations. Actually, that's what the firewall does. Which, by the way, a firewall by a networker's definition does not separate networks, it connects networks. It's isolation which provides security benefit. Usually it's not that much, say, connecting them and filtering at some point. But that is another story. The fourth one is encryption. I'm not sure if I have to explain this one. Fifth one is what we call entity protection. Once you're responsible for the security of an overall environment, the security of certain elements within that environment might play a major role. Number 6, secure management. And number 7 is what we call visibility. Visibility means you should be able, with a certain amount of effort, to understand the security posture of the overall environment or certain elements in it. These, again, principles, from our perspective and from our experience, apply to any kind of complex environment, regardless of the technology, regardless of the size, regardless of the actual setting. It's always those 7 which, say, implementing security can be broken down to. And actually, those 7 can be transformed into a kind of checklist, which we recommend going through once is responsible for securing, say, a complex environment, whatever that may be. Like, okay, can we limit who can take part, be it in the environment or a certain communication act? Is there a need to isolate stuff? What can we do filtering-wise? Where to apply encryption? What about the security of the main elements when it comes, say, to hardening or to security testing or source code review? That would belong to entity protection as well. How to manage the infrastructure and how to provide visibility. So, security in a complex setting can be broken down to applying those 7 principles. It's 7, it's not just one. Hopefully there's not too many people here in the room who think that security can be broken down to system number 4, that is encryption. Unfortunately, there's a number of voice over IP environments where people think, oh, let's just apply encryption and all our security issues might be gone, which is unfortunately not true. As I'll show in a second, we have prepared 4 case studies. I'll go through them very quickly, just to identify the main points. Do not try to read everything that's on the slide. I know it's tempting to look at the slides, not at speaker. Look at me or Daniel or whoever. Try to follow our words, as the main message can be broken down to just some points. In the first environment I'm referring to, and just for the record, some information is obfuscated, obviously, but all these are real security assessment engagements. What you see here is, say, the management interface of a certain voice over IP technology, which in that case was exposed to the corporate network, or to the place where we as the testers were sitting, which was an empty office. This is a violation of the principle of secure management. Second, in the same environment, I mean, voice over IP is not just media gateways or call managers or central voice over IP components, but there's a bunch of stuff around this. Application servers hosting mailboxes, connecting to some CTI functionality, hosting music or recording trading calls and all this. And in that environment, where some of those application servers, the test was performed in early 2011, which is an important info, as the application servers could be easily compromised by this one. Some of you might know this is Configure. So having systems sitting around hosting mailboxes of users in the environment not being patched against Configure in early 2011, that's what we would call a violation of one of those principles, to say the least. So in that environment, there were, say, coming from those 7 principles, there were violations in some of them, and some of those violations led to severe business risks. Namely, the lack of entity protection, lack of hardening and patching of the application servers, and the lack of encryption. Second environment, again, I'll skip the details. What was interesting in the second environment is that the voice over IP stuff itself was in a pretty good security state. We couldn't manage to break into the media gateways. We couldn't manage to even bring them down or so by fuzzing, which is, as some of you might know, a thing we like to do, and we have our own tools for that. What was interesting, again, there were application servers, which again, 2 years after Configure could be compromised by Configure, which is, by the way, that is not so much negligence of, say, sysadmins, but things like these can be broken down to the overall responsibilities in many voice over IP environments. Many organizations have outsourced, say, operations of their voice over IP environments, and the outsourcing party, in some cases, has outsourced even more to, say, a vendor-related or to some organization in proximity to the vendors of the stuff. So there's lots of parties involved, and maybe none of them feels responsible for patching, as long as no SLAs are violated. There might be unclear roles and responsibilities, and this leads to exactly this kind of problems. So it was MS 0867 again, which in that environment meant we grabbed the passwords from one of the compromised boxes, which now turned out to be the passwords for the media gateways and all the other stuff as well. So admin reuse of admin password on all the devices, and the devices which had a good security posture earlier now could be easily compromised once we had a password and the management ports were open to, say, the corporate network. An additional observation was they didn't have any, say, security on an access layer. So if that had been in scope, we would have easily been able to compromise, say, the network from a network level, which at the time led this was one of the triggers for developing Loki, one of our tools. So to long story short, again, while encryption was used and good encryption was used, compromise of, say, the environment and certain assets possible to a lack of entity protection and lack of secure management. Third thing, yet another environment. There we found stuff like this, which is an obviously it's an SSH login into some storage device. That storage device has a well-known vulnerability of a default admin password. As you might figure, having admin access to some storage box in a voice over IP environment might expose quite some assets. Furthermore, we could bring down a certain system by fuzzing it, which was due to the fact that it wasn't running the say a firmware which was known to be vulnerable, which overall leads to an assessment that goes like, okay, once again, even though encryption was used, severe say flaws in the areas of entity protection and secure management. Yet another one. I'll skip this one. It's the same message. Funny thing about this one was it was mostly open source based, but the stuff wasn't patched too well. In the end of the day, we heavily compromised systems responsible for core functions within that voice over IP environment. And again, it can be broken down to failures in the space of entity protection and secure management. So in short, for the first part of the talk, the main message is, and some of you might know, we always, while providing technical talks, we want to deliver, say, a relevant message. This relevant message right now, until here, is voice over IP security can't be broken down to just using crypto. Crypto doesn't solve all your problems, as yeah, you might have already known. It can certainly be helpful in a number of scenarios. But then again, some of you might recall Diffie's keynote yesterday, where he said we have a quite mature state when it comes to algorithms, but we might have, say, a not so stable and good state when it comes to implementation. And this is actually the second part of the big message. Once more, crypto, or as always, crypto has to be broken down, the security of an overall crypto environment to the security of the implementation. And now comes the stuff that certainly most of you have been waiting for, which is we are going to discuss some issues in Cisco's voice over IP technology. This part of the talk again is split into three pieces. Just a short refresher on how certificates work, an overview how certificates are used within Cisco's voice over IP solution, and then yes, things that can go wrong. Short refresher on certificates. Say there's two entities, Alice and Bob. Alice and Bob want to do something securely with each other. They use crypto. One approach can be to use asymmetric crypto, but then there has to be some exchange of keys. And let's assume Alice and Bob were in a shared IP network. They might not trust each other from the first place. So they need a trustworthy third party, a CA, certificate authority. And once this CA comes into place, this CA can sign by some cryptographic operation the combinations of identity plus public keys of the involved parties. And this signed package, I mean, there's more in it, but let's break it down to an identity information plus cryptographic piece, a public key, bundled and signed. This is a digital certificate. There is some say structural problems with this. So how do Alice and Bob know they can trust that party called CA? And there is two main approaches to address this, what is known as the root of trust problem. First one is have yet another party who signs the certificate that CA uses, or deploy the public keys of the relevant CAs in advance, which is what, say, when your browser or operating system brings some certificates along, This is using the second approach. There is a number of network equipment vendors which try to solve both problems with one stone, kind of, by using so-called manufacturing installed certificates. Those are certificates which are brought onto network devices during the manufacturing process, which means once the devices are shipped, first they have a certificate, which is good as they can start doing IP, for example, certificate-based IPsec immediately. And they already did dispose of some, say, trusted entity, which is trusted by being built in from the manufacturing state. In the Cisco world, in the voice over IP space, there are some major components. There's more stuff. We'll break it down to just the most important pieces. Obviously, there's phones. Those phones, in quite some cases, already bring some one of those manufacturing certificates. They get another certificate later on, which is called the locally significant certificate. We'll discuss in a second what a CAPF function is. Then we have central components. The main one is the Cisco Unified Communications Manager or Call Manager, the CUCM, which is the call processing entity. On that box, usually, there runs a certain service, the CAPF, CA policy function, which serves for issuing certificates to the phones. And we have a special item which is called the Certificate Trust List, or CTL in short. And this one is deployed, as we later see, from the CUCM to the phone to provide, say, the public keys bound in certificates for certain elements involved, and to kind of serve as a root of trust, which overall looks makes sense and looks good. Point is, we'll need another, say, 10 to 15 slides with a lot of theory. This is due to the fact that the overall, say, relationships and processes are quite complex. Cisco uses within its enterprise voice over IP solution many types of certificates for many different purposes. For the moment, suffice to say that, say, pretty much everything that happens can be done in a, say, secure and somehow cryptography protected way. And the root of trust problem seems to be solved to some degree by bringing those manufacturing installed certificates into the overall picture. We have to be aware that there's at least 3, for the later part of the talk, important certificates. That is, on the CUCM, there is a certificate that is used for signing the files delivered by the TFTP and for securing the CTLS signaling process later on. Then there is at least one certificate for the CAPF for that certain function, which in itself provides certificates to the phones. So this one serves as a CA. The phones have certificates called the LSCs, locally significant certificates, and there is even more certificates involved. But keep those 3 in mind. Those 3 will become important later on. There is that shortly introduced CTL. That is a list, say in a certain format, that brings certificates for some of these functions from the infrastructure side. And this list is pushed to the phones. And again, this one serves mainly for distributing the pub keys and the certificates of the infrastructure elements. And it serves as a kind of root of trust. To sign the CTL, there is certain tokens needed, which Cisco sells with a certain part number. These are Aladdin tokens, which contain, say, a key pair of some Cisco cert or some Cisco CA, and these are used to sign the CL, which is then deployed to the phones. What is a bit funny about this. I know there's some Cisco people in the room. Please forgive us for this. This is what comes with the with the tokens. I mean, this does not sound entirely convincing, say, for security guys like us. Recommends to store the security tokens in a location that you will remember. If you want to do so, keep one security token in the USB port at all times. When I grew up with a notion of, say, smart cards and physical storage of key pairs, be it on smart cards or tokens, this is not what I learned, how to handle stuff like this. And there's a certain default password. But that said, the CTL itself will play a big role in what is going to come.
Yeah, I hope you can hear me. Yeah. You do. Okay. So in the beginning, we had absolutely no clue what the CTL itself is. So we took a look at the file format. First, it's a binary file format. It is built up out of different TVLs, which we find out later. It's a proprietary format, so there is no documentation available, and it has some signature checksumming stuff built into itself to guarantee it's valid. It's valid. So there is a SHA checksum inside. It's stuffed with some magic crypto header before being ciphered. But anyways, this is a part of the CTL. So this is what it looks like if you open it up in a hex editor. You see there is some cert information in the top and another cert information. There is some crypto inside of the file. And when you look at this hex editor file long enough, you will somehow see that there are certain TLVs. So you always get 1 byte of a type, then it's followed by 2 bytes of a length field, and afterwards you will find the actually value of the field. So there is something like the header version, this is the header length, and so on, so on, so on. There is a serial of some certs inside, and this down here actually is the signature. Okay, so a little bit more theory. In the beginning, when you set up your call manager, this call manager will create 2 certificates. One is we called it the call manager certificate, which is, as you hear, used for signing all the TFTP files and for securing the SIP TLS. And there is also the CAPF certificate. You need to get those 2 certificates into your CTL. This is done by a little Windows software, the CTL client. This one first collects all the certificates from all call manager in your environment. Then it requires one of those Aladdin token. It requires 2 Aladdin token because you can lose one and you always need a backup. And it also gathers the certificates stored on the token. Then all those certificates are bundled together in the trust list. This trust list finally is then signed with the private key stored on the token, and this trust list then is pushed up to all the call managers in your environment.
So, hopefully, is there any questions up to here as for the overall relationship and the different types of certificates involved in the picture? If so, you could ask now. Okay, there's a question.
So you mentioned manufacturer installed certificates earlier. Stated that they were used to solve the root of trust problem and then they haven't appeared.
Yeah, the question was, we mentioned the mix, the manufacturing installed certificates earlier to solve the root of trust problem, which, and we haven't mentioned them right now.
Yeah, it's because they don't solve the root of trust problem.
Yeah, we
they're used to authenticate the telephone when the telephone itself doesn't got a cert installed.
Yeah.
It's just to be sure that it's a Cisco phone that you're talking with.
Okay, this gives a good say passing over to what actually happens now. The setup has been performed. Once now the phones come into play. The initial provisioning of the phone, say, depends on certain factors. So first, we have to distinguish between the version of the call manager used. We focus on call manager 7 as it's the one that is most widely deployed. Call manager version 8 introduced some new entity, the initial trust list, which we have not looked at so far. So let's focus on CUCM version 7, and there is some discrepancy between what we get from the documentation, how the phones should behave in certain cases, and what we actually saw when doing some testing. The way it is, say, going is once the phone initially boots, the phone contacts the TFTP server running on the CUCM. The CUCM sends an initial Ctl file, the one that was generated earlier on by means of the token and bundling the certs. The phone checks if it has a LSC, the locally significant certificate, installed. If that's not the case, it again contacts the CUCM to get what we call, I mean, there is a better term for this, but we call it the partial config file, which has mainly the function to instruct the phone, like, okay, oh, you don't have an LSC, please contact CIPF to get a certificate. And so after that, the phone generates a public private key pair, sends the public key by a somewhat proprietary message to the CIPF. This one gets bundled into a cert and signed, and the certificate is sent back to the phone, which it installs and now has an LSC for its disposal to perform all types of security-rated functions based on certificates in the overall picture. What is a bit interesting is how the some initial certificate looks like that is involved. We have not obfuscated this, so this is some signer, some org. The serial number is a funny one as well. It's 1, 2, 3, 4, 5, 6, 7, 8, and so on. And we do.
Actually, this is the signature of the phone loads themselves. So the firmware which is running on the phones is also signed, but that's a signature on those files.
And we did not check who has the domain some org. So back to what the phones do. Now again, recall phones now have a certificate, an LSC, and at each subsequent boot, the last diagram ended with phone installs LSC and reboots. At each subsequent boot, the phone is supposed to perform the following. Retrieve a CTL to check if there was any changes or updates. In case it's a new CTL, so new key material in it, new certificates, whatever, the phone is supposed to check it if this new CTL is signed by one of those certificates which were part of the earlier CTL, which absolutely from a, say, process and process checking point of view makes sense. The phone is supposed to reject the new CTL if this validation fails and to continue with the old CTL. So the phone is supposed to have, say, valid and initially signed by means of the Aladdin tokens, and so trustworthy crypto material. And this actually applies to a number of phones. We didn't have too many phones for our testing. We have quite a lab. We cannot really identify right now which phones do this or don't. Point is, there is.
Yeah, actually, the phones behave different. So,
some of those.
Some of those. So what they do is they retrieve the CTL, they check if it's an updated one or it's not, and after this validation, there are two different things we saw. The first thing is that the phone detects the CTL is in some case invalid, but by the way, just forgot the old CTL, so it's back to initial provisioning stage, so it got no CTL at all, so no root of trust, it just have to accept any CTL. Or the second case we've seen is that the phone just accepts the new one, so it doesn't detect that we have changed something or that there is a modification on that file at all, which also is very bad. And this looks like this. This is the message log from the soft phone itself, and it just says, yeah, trust list updated. So there is no message like, okay, there is something weird here, maybe you shouldn't trust those trust lists, but you don't see anything, and that's the point. Okay, for the record, the new CTL is accepted. So
just to make this clear, the new CTL, which serves as a root of trust, which is supposed to bring all the certificates, the trustworthy certificate signed by an certificate on one of those tokens, or I mean, with the associated private key to be to point it out correctly. The new CTL is accepted without further notice.
yeah, well, one could think, so what? Yeah, this new CTL, in case, includes all the certificates involved in the cryptographic process, and it could be generated, yeah, by someone else than your trusted COCM. Maybe you remember the sum org. In this case, it would be some other org. So we digged a bit deeper into this and had some thoughts about practical attacks, and this is what we came up with. The prerequisites to really attack this misbehavior is, first you need some man-in-the-middle position. In our demo we will just limit this to up spoofing, because what we have tested so far, Cisco phones react very positive to gratuitous ARP. They just accept them and use them. So ARP spoofing is not a hard thing in this kind of environment. The second thing is you need to provide some TFTP service to deliver the trust list. And yeah, the phone has to somehow reload the CTL, which means it needs to reboot. And speaking of phone reboots, that's not as hard as you might think. We've checked some hard phones, and if you do a simple synflat against a hard phone for 30 to 60 seconds, no matter which port, you can even synflat closed ports, this phone will reboot.
This applies to a number of other vendors too, so this is not, say, Cisco specific.
Yeah, we assume that due to all the TCP synths coming in, the phone is on a so high load that some watchdog or timeouts getting triggered and the phone has to reboot at all. Okay, the next step in our attack scenario is, yeah, use this TFTP service you offer to provide a somehow fake CTL. So what means fake CTL? You have to replace the cryptographic information in this trust list, which means, yeah, just replace all the pub keys, the pub key of the CTL's own signing certificate. So this certificate stored on the token, which is used to sign the trust list. Just replace the public key with some public key you also know the private key to. And also replace the public keys of the call manager certificates, the one for signing the FTP files, as well as the one used for the CUP service. Once you do so, you change the phone's crypto material. That means all signed files downloaded from the TFTP from the call manager now are invalid, because the phone can't just validate the signature on those files. So you also have to modify all those signed files on the fly. Okay, sounds challenging. But what does this mean? What one can do if this succeeds, or what one can't do, is access the phone's local certificate, because this certificate, or the private key to this certificate never leaves the phone. So you can't get this. And also, as the configuration for the phone is encrypted with the LSC's public key, you also can't read the encrypted config. But all other things you could do, which is like, one could think about a cup man in the middle, which means send the phone just a not encrypted config file, which is signed. Tell the phone, yeah, please phone, contact the CUP service. Afterwards, emulate some CUP service and tell the phone, yeah, please phone, forget your LSC. And then come again and get a new LSC. And one could man in the middle those LSC negotiation and, yeah, get somehow the private key for the LSC, at least from the perspective of the call manager. Also, if you're in this position, you can think about man in the middle of the SIP TLS stream, which then leads to all of those nice SIP attacks, which means, yeah, you can sniff the key material for the real-time transport, you could redirect calls, you could tear down calls, and so on and so on. Okay, for the demo, I've written a short tool, which is the Ctl Proxy. It just opens up an TFTP service and serves all the local files, for example, some firmware files or the ringtone or whatever. It also downloads missing files from the call manager. So if the phone requests a file you don't have stored locally, the tool will download it for you from the call manager. And then if the tool sees, okay, the phone is requesting a CTL file, the tool also manipulate this CTL file on the fly. So exchange all the public keys. And if the phone further on requests signed files, the tool also updates the signature on all those files. So they look valid for the phone because they are signed with the private key, where the pub key of is stored inside of the CTL. Okay, a lot of keys here, a lot of crypto. So I will try to do this as a demo. First thing would be force the phone to reboot. For demo purposes, I will use a soft phone because it's more efficient. The next step is get the phone CTL replaced, and then, yeah, do some stuff with that. Okay, I've got a phone ready. So here it is. This is the IP communicator. It's initial provisioned, so it got a valid CTL stored on it. It got an LSC. It's just like ready to use in your company. I also got a call manager on the little box here. So the phone will now connect to the call manager and, yeah, just provision, which is normal case. I don't do any nasty stuff. Just to show you how this works, that it work, if it work. Come on. Yeah, sometimes the soft phone is a bit tricky.
Okay, I mean, this is the part when doing live demos. At least it's not, our laptops have not failed so far. And we have set up enough time for the demo, so we can cope with this as from a talks perspective. Yeah, for the overall setup, to show you what is happening, we will show what is visible on the network from the phone's perspective. Right now there's nothing visible.
Oh.
Okay. It's
out
somehow.
There is some change. So, okay, you see there is some TFTP activity going on. The phone is requesting some files from the call manager. Also, it should get those files. Oh, yeah.
I mean, if, say, initializing phones in your corporate environment would take so long, your users would probably kill you. But we somehow get there. You can see in the
So-
back.
You see the phone is just updating the CTL. So it does this a couple of times during boot up. And come on, it's downloading the encrypted and signed configuration file. And there it goes. Okay, so now the phone is registered with the call manager. You can see all the SIP TLS traffic in the background. So there is the TLS handshake, and afterwards there is only encrypted data streams.
So everything is encrypted right now, from the phone's perspective. Everything looks good.
So I can show you all the status messages. Just says, okay, trust list got updated, and afterwards I got an encrypted and signed configuration file. And if I dial 112, the second phone over here is ringing. So it's provisioned, the call functionality is given, and we can place calls. Everything's fine. This is how it should work. So the next step for an attacker would be to create some man-in-the-middle scenario, which are just some dirty tricks to get all the SIP streams terminated on my local sockets and stuff. Also, I'm launching up a tool just to sniff the SIP data stream. And in a second shell, I will start up the Ctl Proxy, which now serves as a TFTP service. And okay, the phone is gone. I use Loki for ARP spoofing, so once I click the play button, there is some ARP spoofing going on in the background, so we're now actively in a man-in-the-middle position. When I now launch up the phone again, hopefully it doesn't take that long this time. It's even faster. So you will see in the background there is also some TFTP going on, and the Ctl proxy is asked for some files. So the phone tries to download the Ctl file, the trust list, to check if there is an update in. Then the Ctl proxy detects, okay, the phone just requests an Ctl file. I don't got this Ctl file, so I will take it from the call manager, the original Ctl file, and afterwards just modify it. So it's updating the cert which is used to sign this Ctl. It will also update the CAPF cert and the call manager cert itself. After that, the file is patched and signed, so then it's delivered to the phone. And if the phone accepts this file, one would also need to update all signed files, which the tool will also do in later on. So there is some encrypted and signed configuration file. This file is fetched from the call manager, then the signature inside of the file is updated and it's delivered to the phone. So on the phone side, you see there is some TFTP going on, and there is SIP TLS going on, SIP handshake, and encrypted application data. Looks good so far. Also, if we check the log on the phone, you will see, okay, there's another status message saying trust list gets updated, and I also got an encrypted and signed configuration file. So no difference here, just look the same. I also can dial the other phone, and when I answer the phone, there is also this sign over here which says, okay, this is a secured phone call, everything's good, everything's fine, you can talk about whatever you want. So, but meanwhile, in the background, the other tool sees the clear text zip traffic all the time. So there is the initial phone which just registers to the call manager. Afterwards there is register and invite. So the phone makes a call, says, hey, dear call manager, I want to place a call. And by the way, this is my crypto algorithm used on the RTP stream, and there is the inline RTP secret.
So from phone's perspective, everything looks all right, but we have an active man in the middle position now. Everything is, say, clear text for us. As we are sitting in the middle, we have replaced the key material. We have replaced certificates. We are serving, as the tool says, as a Ctl Proxy. The tool will be released soon. At some point, we prolonged the responsible disclosure period with the parties involved. But yeah, it's ready to go, kind of. So yeah, this should, in short, and to make it clear, this should never happen. Exactly, this is a scenario the whole architecture is built to prevent from. Clear text for an attacker in a certain position, everything open. By the way, there would be the username and all this is visible. I mean, it's clear text zip. It's no more zip TLS. For the involved parties, it looks like zip TLS. For the from an attacker's point of view, it's clear text zip due to the replaced certificates. So that's it for the demo. I'll switch back. Hopefully the implications of this got clear to you. Again, instead of cryptographically secured zip and subsequent exchanges, clear text on the attacker's side. So this leaves me with just one slide left. So what should be done to prevent this? There's two steps. I mean, for the say for environments using this stuff, the initial CTA deployment, from our perspective, should be performed in a hopefully trusted environment. And second, to us it seems the algorithm checking what happens. Oh, there's a new CTL. Is this a valid one? How to behave in case this is does not seem a valid one? This algorithm seems not to do not to behave as it is supposed to behave. To summarize, good crypto in the complex settings may be hard to implement. As Diffie said yesterday, the algorithms are there, but the implementation may be somewhat insufficient at points. And to put it into an even bigger context, crypto doesn't solve all your problems. When deploying voice over IP, think of the Seven Sisters, think of an overall risk, say from an overall risk assessment posture, and understand what can happen to the application servers, to the storage devices, to all this stuff being part of your voice over IP environment as well. That's it from our side. Thanks for your time and listening. Any questions? There was several. That gentleman over there. The question was, what is Cisco's response to this? They are working on it. That's how I would phrase it right now, as we committed to say prolong the disclosure, responsible disclosure state. I mean, it's a complex thing. It's not, at least we have not been able to figure out exactly, given the limited size of phone models we had. We tested about five models, including the communicator. Some of them did this, some of them didn't. We can't really spot why this is the case. Maybe there will be a response from them at some point. Right now, they are working on it. There was another question.
So suppose they make the obvious patch and change it so that the phones don't accept a new CTL with a signature that isn't like it was in the old one. How much have they really fixed it? Because it's so, for example, you can still dump phones back into initial config state, and it strikes me as it's a little bit tricky for the phone to correlate, you know, this initial CTL was signed with the erratic key and so forth, with the key it got embedded with, and you know, to not be able to take advantage of that in some way. Have you tried messing with that?
Yeah, the first CTL every phone receives is by definition self-signed. So if you mess up with the initial deployment step, you always win.
But you could also
The question was too long to repeat anyway. So.
also dump phones back into initial deploy state.
Yeah, right. And
That's,
you need physical access to the phone to do so.
yeah, that's why we recommend the do the initial provisioning in a trustworthy environment. From our perspective, solving the problem of accepting a new CTL without validating it correctly against the old one, that would help a lot. That would probably solve, at least for the things we showed, would raise the bar significantly. I mean, the attack is not easy anyway. This would make it even more difficult. Oh, by the way, you might have noticed, some of you, the slides are somewhat different from those on the CD. We polished the optics at some point. There is no, say, additional info in the slide set, which is not on the CD. It's just for the diagrams and stuff. Any more questions? Thanks for listening and enjoy Black Hat.